Hello, welcome back. This is Scholar Strife doing some math. Today will be in Algebra 2, solving exponential functions. Let's see here. Feel like I got this backwards. Yeah, let's go to the third page. Here we go. So I feel like applications are after you learn the basics. Here we go. Exponentiate. Oh, that's the word I was looking for. I've been telling people to base both sides. But basically, you rewrite both sides of an equation for the same base. So, once again, if x equals y, then log base b of x equals log base b of y. And then vice versa, if log base b of x equals log base b of y, then x equals y. With a side note, x, y, and b are positive, and b cannot equal 1. Okay. So for example, if you take the log of something with a certain base of x equals log base 2 of 7, then obviously x equals 7. If x equals 7, then log base 2 of x equals log base 2 of, or 7. You get the idea. Logs on both sides. If logs have the same base, then cancel logs and set the expression equal. Solve the equation. Then we're going to check for extraneous solutions. Alright. Number 10. What? Whatever. Log base 5 of blah 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 equals log base 5 of blah. So, because they have log base 5 on both sides, we can cancel this out. Boom boom. It's kind of like dividing, but remember, but how we would get rid of it is we would exponentiate both sides by having the base as 5, and then they would cancel out. But so now we have 2x squared plus 7x equals negative 12x plus 10. Hey, look, the old basic algebra stuff. Since we have quadratic, or squared, we're moving everything to one side. So I got 2x squared plus 19x. So I'm moving everything to the left. These two, the negative 12x and 10, moving to the left. Minus 10 equals 0. And then this factors to 2x minus 1, x plus 10. Oh no, it's not factoring again. So this equals 0. That means 2x minus 1 equals 0. So x equals 1/2. And then x equals negative 10. Make sure to plug it back in and check. Just use a calculator. You'll be fine. Okay, number 11. Natural log. Boom, boom, boom. So since natural log of one side, natural log of the other, they cancel. 7x minus 4 equals 2x plus 11. 5x equals 15. X equals 3. Make sure to check this out. Okay, what happens if there's only log on one side? So it's on both sides, it's easy. Or at least I hope it's easy for you. With log on one side, we have to condense the logarithms if we need to. Like, condense it so there's only one log that we have to deal with. Then we get the logarithm by itself. Rewrite the equation in exponential form, solve the equation, and remember to check for extraneous solutions. I like how there's two step twos there. Anyways. So log base 2 of x minus 6 equals 5. So it's already condensed as far as we can get it. Get the logarithm by itself. It's already by itself. Rewrite the equation in exponential form. Okay. So exponential form says base is 2 to the 5th equals x minus 6. Okay. So we get 32 equals x minus 6. And so x is 38. And then we're going to do a quick check. Log base 2 of 38 minus 6 equals 5. So we have log base 2 of 32 equals, let's 5. And yes, indeed, that works, so check. Alright, number 13. Negative log. So, there's only one log. It condenses about as much as it can be. So we have to get it by itself. So we're going to subtract 7 over. So we get negative log, or that's a 3. Negative log base 3 of 8x equals equals negative 5. And then there's a negative log, so we're going to divide by negative 1 to both sides. So we'll get log base 3 of 8x equals 5. Okay, and then rewrite it as exponential form. So this is 3 to the 5th equals 8x. So this is 243 divided by 8 equals x. And let's just say that works. Alright, next. Natural log of 3x minus ln natural log of 2 equals 4. There's two natural logs here, so we're going to condense them. Remember, if we're subtracting two logs, that means we take ln of the first over the second. And then set that equal to 4. This is when we're going to e both sides. So what happens, so I'm going to exponentiate both sides by e. So this is e to the ln and e to the 4th. So I get 3x minus 3x over 2 equals e to the 4th. Multiply both sides by 2. And then divide by 3. So I will get 2/3 e to the 4th, which means x equals 36.4-ish, approximately. Yes, you would put this in your calculator. I would do, if you're using your phone, I think it's what? I think it's 4, then e, and then times 2/3. I think that's how it would work. Stop using your phones. Use actual calculators. They're like $10. Come on, $5. You guys don't need the TI-84s until next year, because we got class set. Anyways, log base 5x, or no, log base 10 of 5x, so log of 5x plus log of that equals 2. So remember, if we're adding, that means multiplication. So log of 5x times x minus 1 equals 2. Okay. So this is writing in exponential form, 10 to the second, because this is log base 10. This is secretly log base 10 to the second equals, I'm just going to go ahead and distribute 5x squared minus 5x. So we got 100 here equals 5x squared minus 5x. Let's go ahead and move the 100 over. So I got 5x squared minus 5x minus 100. That's all equal to 0. And oh, yeah, they all share 5. So x squared minus 1x minus 20. And that will reduce to, or factor into, x plus 5? No, x minus 5. X plus 4. So let's try out x equals 5 and x equals negative 4. So if I plug it in, so if I plug this one in into the original equation, cannot do. So this is extraneous, which means it doesn't work. So your correct answer is x equals 5. So once again, if you cannot have a log of a negative number, and if I plugged it into the first or second log, log of 5 times negative 4 is negative 20. You can't have log of a negative number. And once again, log of negative 5. That's not going to work. But the first one works. So x equals 5 is our final answer. Alright, let's go to the next page. Boop. Da, 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 da. Alright, a little summary here. Can be written as same base. So when you're given exponents with the same base, set exponents equal and solve. So if we have 7 to the 3x plus 4 equals 49 to the 2x plus 1. Okay. Now they didn't really go into detail with this example, but this secretly, this 49 here is actually 7 squared. Okay. And then we have the 2x plus 1 here. That gets multiplied. So that does that. So on the left, we'll have 3x plus 4 equals, so 2 times 2 is 4x plus 2. So what happened to the bases? They're the same base, so we can set the exponents equal to each other, and that'll work. And then this would be just a matter of x equals 2. Exponents with different bases. So you would take the log or natural log on each side. Eight to the x equals 20. So if we have 8 to the x equals 20, we would take the log base 8 of both sides. these will cancel and you're left with x equals that mess. Punch in your calculator, get an answer. If you have logs on both sides, that's if they're the same base. If they're the same base, you can just set them equal to each other. You just get rid of the logs, cancel logs, set expressions equal and solve. So let's say if we have log base 5 of 4x plus 9 equals log base 5 of 6x, then we just can get rid of the logs and we'll be left with 4x plus 9. Oh, that looks terrible. Equals 6x. So if you have the log of both base of both sides, if they're the same, then you can just set their insides equal to each other. And then you would solve that. Log is on one side, condense, get it by itself, and then rewrite as exponent. So if we have log base 2 of x minus 4 equals 6, then we get it by itself. It's already condensed. We're going to exponentiate both sides. So 2, 2. So this is 2 to the... So what's happening here is 2 to the log of 2, and then this is 2 to the 6. Those cancel, left with x minus 4 equals 2 to the 6, and then you can solve that. Alright, Richter scale formula. This measures earthquakes, the Richter scale. Find the intensity I as compared with the reference intensity I sub O of the 1906 San Francisco earthquake if it had a Richter number of 8.25. So this is R. We're looking for I. And then I sub O is right here. It's always given to be that number. So we have 8.25 equals log of I, which is what we're looking for, over 10 to the negative 3. Okay. So, I'm going to exponentiate both sides because this is base 10. And what's going to happen is we're going to have 10 to the 8.25 here equals 10 to the log of base 10. So that cancels. And I'm left with I divided by 10 to the negative third. Okay, multiply both sides by 10 to the negative third, we'll get 10 to the 5.25 equals I. Did I do that right? And then punch in your calculator. Where is my calculator? Alright, it's 10 to the 5.25. Yes. This is 177,827.941. That's the intensity. That's pretty big. You know, the Richter scale 8.25. That's, yeah, it's a large earthquake. Okay. Next page. Let's go back up. I wasn't sure which one's going to be first. I mean, this does say A, but this is the Richter scale. I just feel like these would be last because they're applications. That's how the book normally does it. You learn how to do the equations, you know, just random numbers, and then you apply something real. So here's your exponential example, and then here's your log example. Newton's law of cooling describes cooling of a warm object to a cooler temperature of the environment, or warming up if it's a warm environment. Richter scale, we just did it. Earthquake number depends on the ratio of the intensity of the earthquake versus the reference intensity, which is the smallest earth movement that can be recorded on a seismograph. Property of equality for exponential equations. I could have sworn I just did this. Did I do this? Yeah, this is the whole... Oh, exponential. Before it was log. This one is if x equals y, then b to the x equals b to the y. And b must be positive. Oh. So, for example, if we have 3 to the x equals 3 to the y, oh, 3 to the 5, I wonder what x is. It's obviously 5. And vice versa, if x equals 5, then obviously 3 to the equals 3 to the 5. So if possible, rewrite the bases so that they are the same. Okay. So 9 to the 2x equals 27 to the x minus 1. Okay, this is secretly, this 27 is 9. Nope, sorry. This is secretly 3 cubed, and this is secretly 3 squared. Okay? Now you gotta be careful, because yes, this is 3 squared, but what happens to the 2x? The 2x is still up there. It just gets multiplied. So this is equals 3 to the cubed, put this in parentheses, x minus 1. Okay? So this is 3 to the 4x, because remember that we multiplied, equals 3 to the 3x minus 3. And remember that was distributive property. So now we can set the exponents equal to each other. 4x equals 3x minus 3. So we're left with x equals, if we subtract 3x over, x equals negative 3. What's wrong with my pen today? 3. Okay, number 2. You have to recognize that 1/3 is secretly 3 to the negative 1. So this is 3 to the x equals 3 to the negative x minus 3. That's distributing negative 1 to these two numbers. So x equals negative x minus 3. So 2x equals negative 3. So x equals negative 3 halves. Number 3. This 81 is secretly 3 to the 4th. This is 3 to the negative 1. So this is 3 to the... Is that an 8 there? No, let's see what that is. That's a 3. So that's 4 times 3, which is 12, minus 4x, equals 3 to the negative 5x plus 6. So 12 minus 4x equals negative 5x plus 6. Gonna add 5 over, so I get x equals negative 6. Alright, let's say if we have different bases, then we take a log and go to sleep. Take a logarithm on each side. Okay, use a number for the base that is equal to the... Here, use same base. We'll just go through example. 2 to the x equals 5. They're not the same base. We can't make them the same base. So we take the log base 2 of both sides. So what happens is we have log base 2 of 2 to the x equals log base 2 of 5. Boom. So that is left with x equals this. Now from last section, 7.5, we have that change of base formula. So remember how it goes is x equals log of 5 over log of 2. And now that you can punch in your calculator, so you'll get x is 2.322. Now if you have a fancy calculator, you can use you can just punch it in like before but most standard calculators or scientific calculators, they do not let you easily change the base. They use log base 10. Alright, next problem. 7 to the 9x equals 15. Take the log base 7 on both sides. So I'll get 9x equals log base 7 of 15. So x is going to equal log of 15 over log of 7. And we're dividing all that by 9. Yeah, this 9 here. So we'll get, I don't know, 0.155 about. Alright, and then remember base E for e to the negative 0.3x. Remember, always get your exponent by itself. So we're going to add 7 over and get 20. And then divide by 4. So now we have e to the negative 0.3x equals 5. We're going to do the natural log. That's the opposite of e. So natural log of both sides. So ln of e to the negative 0.3x equals ln of 5. Those will cancel, so I'm left with negative 0.3x equals ln of 5. And divide by negative 0.3, and we'll get about negative 5.365. Okay. One more page, and then we'll be good to go. Word problems. Yes. You deposit $800 in an account that pays 0.5 interest compounded monthly. So compounded monthly means we're using this formula. Principal times 1 plus r over n over to the nt. Okay, so deposit $800 p. R.005. Wait. Yeah, 2 decimal places. 0.005 for R. And then monthly means 12. How long will it take to grow to 1,000? Okay. And then let's put A here. So this is 1,000 now, equals 800 times 1 plus 0.005 over 12 to the 12t. Okay. So let's let's move that 800 over by dividing it. So I'll divide both sides by 800. And I'll get 1.25, and then I'm going to simplify this inside number. This is 1.000417 to the 12t. Okay. So we are going to log base 1.000417 both sides. Okay. So we're going to be left with, on the left side, we're going to be left with log base, 1.00417 of 1.25 equals, on the right, it'll cancel, so 12t. So we use our change of base. And you gotta obviously use a calculator for this one. Log 1.25 over log 1.000417 equals 12t. And then whatever you get, you divide that by 12. So t is about 44.6 years. So that is a terrible annual interest. Takes 44.6 years. Just to grow $200, you know, it's really terrible. So now we can finally work backwards without, having to graph it using some graphing implement, and then we have to actually look for it. Like 44 years, we wouldn't think it's like, it would take that long. Especially if you don't have any experience working with these equations. Alright, Newton's law of cooling. Hot chocolate that has been heated to 90 degrees Celsius, poured into a mug, and placed on a table in a room with a temperature of 22. So room temp is 20 degrees Celsius. If R is 0.145, when the time t is measured in minutes, how long will it take the hot chocolate to cool for a temperature of 30 degrees Celsius? Okay. So we have T, temperature of the object at time T. So we want to know when it reaches 30 degrees Celsius. And we set that equal to the initial temperature of the object, which is 90 degrees Celsius. So parentheses 90 minus TR. Constant temperature of the environment, so room temperature is 20, and then E to the negative R, rate of cooling, negative RT, so negative 0.145, T was what we're looking for. So let me write that again. So E to the negative 1.45 T plus TR, which is once again room temperature, 20 degrees Celsius. So get rid of those degrees. And make sure you're working in Celsius, and make sure it's all Celsius, otherwise convert. Okay. So once again, this is 30, this is 90, this is 20, this is 0.145, And time is what we're looking for. Okay. So I'm going to move this 20 over the other side by subtracting it. So I'll get 10 equals, clean up the parentheses, 70 e to the negative 1.45 t. Divide by 70 to both sides. And I'll get 1 over 7 equals e to the negative 1.45 t. Take the natural log of both sides. So you have natural log of 1/7 equals... Boop. Negative 1.45 t. Divide by that, and we'll get t is... Oh, this is in minutes. 13.42 minutes. Alright, and then another application of this stuff. The CSI guys. A detective is called in the scene of crime where a dead body has just been found. She arrives at the scene at 10:23 p.m. Usually any number should be like circled or underlined. Immediately the temperature of the body is taken and is found to be 80 degrees Fahrenheit. The detective checks the thermostat and finds the room has been kept at a constant 68 degrees Fahrenheit. I guess this formula works for Fahrenheit as well, as long as you keep it all Fahrenheit. Is that what I'm guessing here? Yes. So it's either all Fahrenheit or all Celsius. So, mistake I made before. I thought it was all Celsius. Usually it deals with that, but I guess this formula works for both. The next day, the detective is asked by another investigator what time did our victim die. Assuming that the body temperature was normal, 98.6 prior to death, and cooled at a rate of 0.134 degrees Fahrenheit per hour, what is her answer to this question? So, T, 98.6, time of death, equals the... Oh, no. Sorry. Time of death is not the T. That's the initial. Okay, so let's just write out all our stuff. T, T dot, TR, R, and T. So we know this is 10:23, but no, sorry. This is what we're looking for. What time did he die? The rate is 0.134. Temperature of the room, 68 degrees. What time? 98.6 for initially before death, or time of death. And then it got a little bit colder, 80 degrees. Okay. So, 80 equals 98.6 minus 68 e to the negative 0.134 t. So this is per hour. That means our t is going to be in hours. Okay, we're just going to do what we did last time. Oh yeah, plus the original room temperature again, which is 68. So subtract 68 from both sides, we'll get 12 equals 30.6 e to the negative 0.134 t. Divide by 36 to both sides, 30.6. Okay, and then we're gonna get some crazy decimals. Natural log both sides. Natural log of 0.3922 equals negative 0.134 t. Divide by that, and we'll get t is around 7 hours. So they looked at the victim at 10:23 p.m. So they looked at 10:23 p.m. So 7 hours ago would be 3 o'clock, 3:23 p.m. So about that time. Okay. Some really applicable stuff, right? Alright. Hope you had... I mean, throughout this chapter, you just learned about log, and there's like no application inside, and you're like, what is this? Why do we learn this? And then here's some actual applications. Have a good day.